years later, nobody has done that. It is not a scientifically viable solution. But in the future, decades from now, it may be possible that we can solve these problems. You see, the problem is ice crystals. Once you freeze the human body, ice crystals form inside a cell, grow, and rupture the cell wall. So if you are thawed out after being frozen solid, then you have basically a bunch of mush, protoplasm that is dead because cell walls have been ruptured. Now, that's not to say that centuries from now we may perfect this technology. Then it becomes a viable option. Now, another option is to lengthen the human lifespan. We are now on the verge of understanding the aging process. Just 20 years ago, people would have laughed if I said that. Now we know how aging takes place. Aging is a function of air buildup in a cell, genetic, molecular, cellular error. But errors can be corrected because we have correction mechanisms. For example, the Greenland shark lives to be over 400 years of age. Think about that. Just because of genetics, it's possible that an organism on the Earth, genetically modified, can live 400 years like the Greenland shark. And we're now beginning to identify the genes that are responsible for longevity. So to sum up, to answer your question, yes, you're right. To go to the stars, we would have to have a new way to either lengthen the human lifespan or freeze the human lifespan to transit these directions, to these enormous distances. Now, beyond that, when we become a type 2 civilization, there is the other option, and that option is warp drive. However, that's a whole nother question, but that's what I do for a living, to work on Einstein's theory of general relativity and the quantum theory, which make possible warp drive.
Okay, Justin Olson asks, and this is related, will it ever be possible to intentionally stall or stop time to travel great distances?
Well, in some sense, we can already do that, in the sense that when you're in a rocket ship and you go toward the speed of light, time slows down. So in principle, if you are near the speed of light, time stops inside your rocket ship. Now you may say to yourself, well, that's preposterous, right? No, we measure that with our laboratory instruments. You can put a clock, an atomic clock, on an airplane. The airplane takes off and it communicates with a twin clock on the planet Earth, and bingo! You can see right there, right in your laboratory, the fact that the clock in the airplane beats slower than the clock on the planet Earth. So our astronauts who travel at 18,000 miles per hour, they are a fraction of a second younger by going into outer space. They are, in some sense, time travelers. Now, of course, that's not a real time travel. They simply go microseconds into the future. People want to go into the past, and that, of course, is much more difficult. We have to apply Einstein's general theory of relativity, which do allow for time travel. Believe it or not, in 1949, one of Einstein's roommates at the Institute for Advanced Study, Kurt Gödel, one of the greatest mathematicians of the century, found a solution of Einstein's equations which allow for time travel, going backwards in time. Gödel found that if the universe rotated and you went around the universe as it rotated, you could come back yesterday. You could come back before you left. You could become a time traveler. Now, Einstein himself in his memoirs was very worried about this. Einstein himself was very wary of time travel. But in his memoirs, Einstein writes that, yes, his equations do allow for time travel, but we can dismiss it on physical grounds. In other words, the universe expands but does not rotate. Now, if the universe did rotate, it would mean that time travel would be an ordinary occurrence. You could simply zip around the universe and go backwards and come back yesterday. Well, today we have other designs for time travel, but again, that's a whole other book. Go to my book, Physics of the Impossible, where I have a whole discussion of time travel into the past.
James Bridges asks, what's the future of anti-gravity technology?
Well, a lot of people say going to the stars, planets, using starships, well, it's no big deal because all you have to have is antimatter, anti-gravity ships and anti-gravity propulsion. That's the cure for everything. Well, no, it doesn't work that way. First of all, antimatter is the opposite of matter with the opposite charge. An electron has negative charge. We learned that in high school. But the anti-electron has positive charge. Now, what about light? It turns out that light is its own antiparticle. Anti-light is light. Now, gravity, we think, is mediated by gravitons, and we think, therefore, that anti-gravity is given to us by gravitons. So gravity and gravitons are the same thing, just like light and anti-light are also the same thing. So don't expect to create anti-gravity drive by creating the mirror image of gravity. Now, what about the Big Bang? What is pulling the galaxies apart? There must be an anti-gravity responsible for the expansion of the universe, and that is dark energy. It turns out that dark energy is slightly anti-gravitational. It is pushing the galaxies apart, and it's the energy of the Big Bang. People sometimes say, what is the energy driving the Big Bang? It is dark energy, the energy of the vacuum. But it is very small, very tiny, sometimes called zero-point energy. It's simply too small for a propulsion system. So to summarize, anti-gravity drive is not possible because anti-gravity is the same thing as gravity. There is something called dark energy, which does have anti-gravitational properties. It pushes galaxies apart, but it's simply too weak to create a rocket ship. So once again, we're stuck with rocket ships that use fusion, ramjet fusion engines, or antimatter, or perhaps maybe a form of warp drive, but unfortunately, no anti-gravity. Sorry about that.
Okay, Antoine Najum asks, what do you think of Elon Musk's belief that the universe is a holographic simulation projected by some computer program?
Well, many people saw the movie The Matrix. And in The Matrix, reality itself was a memory uploaded into the human brain. And then people said to themselves, aha, if you could upload reality, a fiction, into somebody's brain, maybe reality itself is a fiction. Maybe we live in a simulation. Well, yes and no. First of all, let's talk about simulations. We try to simulate the weather. This is a multi-billion-dollar industry to predict the weather. But there are so many particles of air, molecules that move according to Newtonian mechanics, that the smallest object that can model the weather, the smallest thing that can model the weather is the weather itself. No computer is powerful enough to manipulate and calculate the motion of all these molecules to predict tomorrow's weather. Now, quantum mechanics makes it even worse because now we have uncertainty. So with billiard balls, assuming that atoms are billiard balls, you can predict the motion of billiard balls maybe a few seconds into the future, but the weather has so many particles you can't do it. But quantum particles have even more possibilities. In quantum mechanics, electrons can be two places at the same time. Electrons can disappear, reappear someplace else, and you cannot model that with a computer. Therefore, I'm going to say that I don't believe reality is a simulation. That is, the smallest object that can simulate the universe is the universe itself. So in other words, there's no super deity with a super CD-ROM. You push the button, the play button, and here we are, living inside somebody's PC. No, I don't think that's possible because of quantum mechanics.
All right, so somewhat related to weather, Beverly McCarthy asks, what about the astronomers that claim the entire solar system is warming? Is there any truth to this?
Well, yes and no. First of all, Venus is the greenhouse planet. The greenhouse effect is not a fiction because we see an entire planet, our twin, Venus, having temperatures of 900 degrees Fahrenheit, hotter than a baker's oven, hotter than the melting point of most metals. If you were to walk on the surface of Venus, you would sink into pools of molten metal. That's just the surface of Venus. Now, why? Well, first, the atmosphere is made out of carbon dioxide, which is a greenhouse gas. Second, it's closer to the sun, and it captures the sunlight until there was a runaway greenhouse effect. So as far as Venus is concerned, yes, Venus has heated up because of the greenhouse effect. That's a warning to us. The Earth could also warm up in a similar way if we don't watch out. But the other planets, beyond that, Mars is rather cold. It has a greenhouse effect. It would even be colder if it didn't have a greenhouse effect, but it's still very cold. The greenhouse effect on Mars is not big enough to warm it up to room temperature. But beyond that, things are very cold. And so I think you could say that as far as Venus is concerned, things are heating up. But as far as the rest of the solar system is concerned, it's pretty much stable.
Okay, moving on. You discuss in various places this topic. Michio Kaku asks, in teleportation, what would happen to consciousness?
Well, teleportation is a dream of many science fiction fans ever since they saw Star Trek. And if you were to interview Gene Roddenberry when he was alive about why he introduced teleportation, it's because, well, it was too expensive to have the rockets land and take off. Why not simply zap them down to the planet? So in other words, it was budget cuts. Budget cuts at Paramount Studios that forced Gene Roddenberry to introduce teleportation. But now it's part of our life. We dream of being able to zap ourselves. There's even a movie, I think, called Jumpers, where you can teleport rapidly from point A to point B. Now, we physicists have achieved quantum teleportation in the laboratory. That is, if I have an atom of rubidium, I can actually teleport its information to another atom of rubidium. So I have two atoms that are quantum mechanically the same. So quantum teleportation is here and now. We do it. In principle, we can teleport an atom to the moon. We haven't done it yet, but it's definitely theoretically possible. Now, to teleport Captain Kirk, however, is a whole different ball of wax. There are trillions of untold trillions of atoms inside our human body. We have difficulty teleporting one atom across a room, let alone trillions upon trillions of atoms across a room. So in other words, teleportation is in principle possible, but in practice, it simply boggles the mind. It's not a technology that we can harness anytime soon. Now, let's say we do achieve it, though, sometime in the far future. What about consciousness? Well, if atom for atom, you were to create a copy of the human brain someplace else, then is your consciousness therefore transported? Well, it depends on what you mean by consciousness. During the Middle Ages, we had a theory called dualism. In dualism, the soul was separate from the body. That's why it was called dualism. Then came neuroscience in the 20th century, which says, bah, humbug, there's only neurons, just neurons in the body. But now we're going back to the Middle Ages. Now we realize that we can digitize the mind. We can take a human mind or human life, digitize it, all your credit card transactions, all your Instagrams, all your videotapes, everything about you known on the web can be digitized to create a carbon copy of you. And I think in the future, when you go to the library, instead of taking out a book about Winston Churchill, you'll talk to Winston Churchill. A holographic image will emerge with the memories, the mannerisms, everything known about Winston Churchill. And I wouldn't mind talking to Einstein. I'd love a conversation at the library talking to Albert Einstein. So that means the soul can be digitized to a degree. Now then the question is that really you if you digitize the human brain or you teleport somebody? Well, to paraphrase Bill Clinton, it all depends on how you define you. If you define you as a biological entity, then yes, all these copies are fakes. But if you is the sum total of